Let me start with a small teaser. We discussed index. Yes, what is index? It's dimension of kernel. And instead of dimension co-kernel, we use dimension of kernel of formal adjoint. And this is a number which represents some analytical properties of the operator D. And we are going to discuss the following formula. This one is a hat genus of the manifold M. So it's non-homogeneous cohomological class. We already wrote it, but I will remind you what it is a little bit later. More interesting thing is this expression. And we need to discuss what does it mean. It's a very complicated thing and is related to Clifford algebras, blah, 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 Clifford bundles, and so on. So we need to discuss the ingredient. This one is the last ingredient of the Atiyah-Zinger formula, which we do not understand yet. So we know what is an index. We know what is a formal adjoint. D is a Dirac type operator. And right-hand side is a differential form. We take an integral and obtain the answer. The tricky part is that in many standard cases, then the Dirac operator is more or less used for Hodge-de-Rham operator and something like that. Then right-hand side can be written in explicit terms. It can be written as Hirzebruch genus or maybe Todd genus and something like that. But this is the most general formula, which is written in local terms, as a differential forms. So this is a teaser. We need to pay attention to this guy because it's something strange. Chern character E/S, very specific S. You never seen that before. Let me start. We have calculated last time the following thing. We mapped Clifford algebra to exterior algebra by defining the action of this thing here. So first of all, we send this guy to endomorphisms by the following formula. So if you take a vector, then the vector acts here by the following formula. Differential form is sent to exterior product with V minus interior product with Hermitian conjugate to V, substitution to, oh well, sorry, it's not W, it's omega. It was a map from Clifford algebra to endomorphisms of exterior algebra. And if we want to define C, then we send CV to its value of the endomorphism on 1. This was done last time. What I want to discuss today, it is a construction of Spinor representation. Of what? I will write it in this way. ℂ with this sign means that I want to take complexification. So I take Clifford algebra and pass to its complexification. It can be represented by V and the metric. Maybe just we can write just a number. If I don't want to specify, so this is Clifford of Rn with standard Euclidean metric, and then taking tensor product. How many scalar products you know in complex vector space? Not too many, I think one, if it's non-degenerate. So there is only one Clifford algebra. So then you speak about real case, then people usually write two indices. One indicates the dimension of positive part of the quadratic form. This stands for negative part of quadratic form. But in complex case, it doesn't matter, because plus and minus are the same. You can multiply everything by I. That's why we used only one index. So let me start with a couple of simple statements. What is ℂ₂ How can we define it? Your suggestions? It has one generator, yes, and with relation of the form, you can choose +1 or -1. It doesn't matter. Over complex numbers, they are the same. Just make a choice. Because then I make a choice, I make a mistake in the calculations after that. So we need to choose something, and then we proceed with new formulas. +1 or -1? -1. Okay. -1. Okay. Very good. So what is that? If I write this one, then Clifford 1 is complex numbers, tensor product with complex numbers. What is it? It's over reals. This is isomorphic to C plus C. Yes? Very good. Very good. So I want to prove the following formula. ℂn plus 2 is isomorphic to ℂn tensor product with ℂ2. By the way, what is ℂ2? Complex Clifford algebra with number 2. You can think about it in two different ways. First of all, you can take usual Clifford algebra to 0 and then pass to complex numbers, complexification, so it's tensor product of quaternions with complex numbers. Or you can take ℂ1 tensor C. This is a matrices 2 by 2 with real entries tensor with C. So these are matrices 2 by 2 with complex entries. I think it's nice exercise to check that if you take quaternions and pass to complexification, then you obtain matrices. So this would be an exercise for you. Theorem. This is a theorem. I want to prove this isomorphism. Sorry. This is over C. Otherwise, the dimension will be a little bit different. So let me prove that. So this thing, which is written here, exhibits periodicity with period 2. Some of you study topology, and I know that you know what is periodicity with period 2 in topology.
What periodicity?
Yes, sure. This guy is related to both periodicity. If you look for real Clifford algebras, then they exhibit 8 periodicity. It's also related to periodicity in real K-theory. Okay, so we need to prove this isomorphism in more or less direct way. How to do it? What is it? This guy is defined by elements and relations ek, em. Okay, el is minus el ek, and also ek squared is equal. Now you make a choice. What you want to see as a defining relations. First of all, skew commutativity you cannot read off, so it's important. But then you speak about square of a generator. You can choose +1 or -1. Any choice is equivalent to another. But please make a choice. What do you want to see as a square of generator ek? +1 or -1?
+1 seems convenient.
Hmm?
+1 seems convenient.
Are we happy about +1?
Okay, I see.
Okay, 1. Okay, 1. I am not happy because square scalar norm of this element will be -1.
Okay, then.
-1. Let it be -1. I will be more comfortable with it. So, what is written here? What we have here? We have here generators f1, etc., fn, same relations. And here we have generators g1, g2, same relations. What I want to do, I want to send, map R n plus 2 to Clifford n tensor Clifford 2, and I will do it by very specific formulas. What are the formulas? Namely, if I take en plus 1, I will send it to 1 tensor g1. En plus 2 is sent to 1 tensor g2. This is a very good idea because square of this element is -1, square of this element is also -1, same here. They are skew commutative, these are also skew commutative. That's why on these two elements the map is well behaved with respect to relations in Clifford algebras. But it's more interesting what happens if I try to send ej for j from 1 to n to some element here. It's not a good idea to write something fj tensor 1. Who can guess why this is wrong idea? Let me repeat what I'm doing. I send vectors from Rn plus 2 to this Clifford algebra. I will check that scalar product of these elements, which give me relations in Clifford algebra, are satisfied here. After that, I will obtain map from Clifford algebra defined by this guy to this tensor product of two Clifford algebras. After that, I will check that this is isomorphism by calculating dimensions. But the problem is that if I send basis vector ej to this vector, fj tensor 1, then some relations are broken. Please tell me which relations are broken.
It commutes with en plus 1.
Yes, this guy commutes with these two elements. I should not commute. How to do it? Instead of this, we write fj tensor g1, g2. Let me check a couple of things. I will erase the top. I need to check that this element skew commutes with this one. let's think about that. Fj tensor G1, G2, multiplication with, say, G1, same elements, but in different order. Well, that's wrong, just G1. Let's calculate. What is written here? Fj tensor G1, G2, G1. What can you say about this thing? One interchange of letters give me minus, G1 squared gives me minus, so this is just G2. And here we have Fj tensor G1, G1, G2, and this is minus G2. It's okay. It's skew commutative. So up to sign, and here we have plus, here we have minus, everything is okay. Now I need to check that the image of these guys is skew commutative. Let me check it by, I will write it in very explicit way. I will take F1 and F2. Let me simplify it. What happens? So this one is F1, F2, and then G1, G2, G1, G2. We change order here. We obtain minus. Then it disappears, then that disappears. It gives me -1. And if I write them in reverse order, I will obtain F2, F1 tensor -1. So it's also skew commutes because these two elements differ. Their signs are different. So it seems that I checked everything. What do you think about that? Is it okay or not? I think yes. Well, so after that I obtain map from Clifford, complex Clifford algebra n+2 to complex 2. Now we calculate dimensions of this guy. Dimensions of this Clifford algebra over C is 2 to the power of n. And here is 2 to the power of 2. Here we have, then you take tensor product, dimensions are multiplied. So by dimension reason, it looks like they are isomorphic. Their dimensions are the same. Therefore, to prove that they are isomorphic indeed, we need to check one of two very simple questions from linear algebra. We should prove that either kernel of this map is 0 or image of this thing coincides with this one. I believe that to prove that this guy is onto is much easier than to check that kernel is 0, as usual. How to check that this is a map, this map is epimorphic? How to do it? Very simple. We need to show that every generator in this algebra belongs to the image. This one is an image. This one is also an image. How to check that Fj tensor 1 belongs to which element is sent to Fj tensor 1? Up to scalar multiple, it doesn't matter.
Ej, En+1, En+2?
Yes. Fj, En+1, oh sorry, Ej, En+1, En+2 is sent to plus minus Fj tensor 1. We don't care about sign, it's okay. What is left? There is one gap in my reasoning. Remind, I told you that real Clifford algebra is 8 periodic. real Clifford algebra is 8 periodic, and complex Clifford algebra is 2 periodic. My arguments can be applied to real case also. If it's true, then real Clifford algebra also will be 2 periodic, and we will obtain, presumably, maybe we could obtain periodicity in real K theory with period 2, but we know that it is 8 periodic. What is left to check?
But in real case we have more relations. Some K squared are ones.
No, okay, imagine we deal with the algebra which is Clifford n plus 2, 0, n, 0. So I work with first two vectors, maybe, so I can write n plus 2, q, n, q, because nothing difficult here. Where is the gap? Very small gap. I hide it. It's a little bit hidden, but everything is written on the blackboard. Well, there is a small mistake. Not mistake. I did not set something important.
Did we check the squares?
Sorry?
Did we check the squares of?
Yes, we didn't check that squares are okay. We didn't check that squares are okay. So if we're okay, everything is written here. Let me write here f1. f1. We obtain plus 1. Oops. Relations are broken. Not one, exactly n relations for f1, blah, 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 fn. Relations are not okay, because square of this element should be minus 1, but square of this element is plus 1. What to do? The remedy is very simple. It should be complex remedy. In complex world, we add here I. Now we see difference between world of real Clifford algebras and world of complex Clifford algebras. In complex world, we can add here I. In real world, it's impossible. Okay, very good.
A related question.
Okay.
I have missed the first part of the lecture. Is it the same to take complexification of real Clifford and to take Clifford of the opaque?
Yes, it's the same.
With complexified
Because you have generators and you have relations. The tricky part is that when you speak about relations and complex Clifford, you don't care about sign at the square, but you need to choose something to write formulas. But
in other words, two Cliffords with d plus q equals n have the same complexification.
Yes. Okay, gentlemen, we have very good thing. We know that this guy is 2 periodic. We know that for small values of index n, this is either matrices or sum of 2 complex numbers, algebras of complex numbers. So I want to write the statement which can be easily proved by induction. Complexified Clifford 2n is isomorphic to what? You subtract 2, then you subtract 2, then you subtract 2 until you obtain 0. So you have matrices 2 by 2 with complex entries. There are how many of them? N times. It means that you have matrices. Tensor product of 2 algebras of matrices is just Kronecker product. No problem. So 2 to the power of n. Okay? Clifford algebra, this one is just algebra of matrices, but reorganized in some specific way. If you want, you can write generators for this algebra decomposed in this way, and then you find by this isomorphism to which elements of this Clifford algebra correspond concrete matrices. It's not very simple idea, but it's possible. In some books, people do it. So they take generator and then they write you in more or less explicit form the matrix which corresponds to the generator through these isomorphisms. I don't think it's a nice idea. It looks very unpleasing. Okay, next question. What can we say about Clifford of such type? Very simple. If you take Clifford 1, it's just C plus C. And then you take tensor products with algebras of matrices. My question to you is how many times? Why I'll erase, you can say me how many times should I write algebra of matrices. Yes. N times. And then you obtain that this guy is isomorphic to two copies of matrix algebra. Quite simple. In real case, you will obtain 8 possibilities. Matrices or 2 copies of matrices over complex numbers, over reals, and over quaternions. So there are many possibilities. Okay, next question. How many representations of matrix algebra do you know?
Only one irreducible.
Okay, in this question has very simple answer, infinitely many. If you have at least one representation, then immediately you take sum of that and you obtain infinitely many representations. But if I add here irreducible, then there is one representation. Which one? You just this guy acts on this space. Namely, it acts on the first column of this matrix, on the second column of this matrix, blah, blah, blah. They are the same. So let me say that this representation is Spinor representation. Of what? Of? Cool. It should be even dimensional. In some books, people write spinorial. But I will tell that it is Spinor representation. What is important? What is very important here? I want to you know that last time we spoke about that this guy is graded algebra. It contains even and odd elements, and blah, 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 and this grading is behaving well with product here. So it's natural to ask, what can we say about this thing? Maybe this guy is also graded. Maybe it can be split into even and odd part. The answer is yes, and I will show you how to do it. The statement is, I'm very sorry, I need to change the notation. So V will be of dimension n, which is equal to m. What I want to say that if I will explain you how to introduce grading on this. So why I write here V instead of writing just dimension? Because the construction is coordinate free. You can take Clifford algebra, then this thing is unique, more or less uniquely defined as unique irreducible representation. If you choose coordinates, you will obtain them in this way. But if you change the coordinates inside representation will be changed accordingly, because it's representation, say, in the first column of the matrix. If you change the coordinates, what's happening? Two matrices for changing coordinates and one matrix to change coordinates inside the irreducible representation. Okay, so this one is an isomorphism. So I need to explain you how to split this thing into positive and negative parts. Dimension of this thing is 2n minus 1. Yes, is it? Yes, very good. Dimension of S is 2 to the power of m. So I wrote n earlier, now I write m. So how to find this splitting? So what is important? This guy acts here, and this is okay, it's isomorphism, blah, 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 but I want to say that Clifford algebra is graded, and I want to consider not endomorphisms of this thing, but graded endomorphisms. I need to split them into the odd and even part. So how I do it? Let me tell you one interesting thing. Statement. If you take Clifford algebra, okay, for simplicity we speak about complex Clifford algebra, with number n, and here I will consider only even part. So this is an even subalgebra of Clifford algebra. My claim is that this guy, it's 1/2 of the algebra, that this guy is isomorphic to Clifford algebra with number n minus 1 without grading. We do not take grading into account. How to prove it? Very simple. Very simple. Okay, we need to consider mapping from this one to that one or in another direction. What you choose? This one or that one?
From right to left.
From right to left is much easier to do it. So we want to send Rn minus 1 or Cn minus 1 to Clifford algebra, but into even part. And then we need to explain why the generators are represented. So take basis E1 blah 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 En minus 1 here and F1 blah 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 Fn here. What I need to do? I need to send Ej to some even element in the right algebra, in the algebra right hand side. Make your choice.
EJFN.
FJFN. This guy is even, obviously. Now let me check that what we need to check? We need to check skew commutativity. Okay, we write fj fn, fk fn. So what we do? We interchange the order here. So this guy is minus fj fk, fn squared. Fn squared is minus 1, so this one is fj fk. Okay. So if you write the same thing in reversed order, so you take product fk fn and then fj fn. By the same calculation, you will obtain fk fj. It's okay. This guy indeed skew commutative. I will not try to cheat on you, so I will check it by myself. The square of this element should be equal to minus 1. By the same calculation, we obtain fj squared, which is minus 1. Okay. So you are right. This one is a good formula. We send this guy to that guy, this space to the algebra, and all relations are okay. So this map induces map of Clifford algebra with number n minus 1 to even part of the Clifford algebra n. But I want to prove that this is an isomorphism. Is it true that I obtained here epimorphism? So the dimensions are okay. So this one is 2 to the power n minus 1, and this guy is 1/2 of 2 to the power of n. The dimensions are the same. So to prove that this is an isomorphism, I need to check that this one is linear isomorphism. So I need to check that it is. I believe it's much easier to prove that this is onto. Okay, how to prove that this is onto? I need to check that generators are in the image. Your suggestions?
I think the generators are already written on the.
Sure. This element is an image because I proved it. But even part is generated by products of pairwise products in any order. Okay, so these are generators and these are generators. They are all generators are already in the image. Okay, let us consider. So instead of, so we know that Clifford algebra, Clifford V, acts on Spinor representation. But now I want to restrict this guy to smaller subalgebra, which is ℂl₂ Okay, ℂl₂. This guy still acts here. But you can imagine if you make the algebra smaller, so the collection of operators became smaller, then in this space, it's possible, it's not guaranteed, but it's possible that now inside this space you will obtain invariance of spaces. And this representation became reducible. What do you think about that? Okay, don't want to write here 2m, even part of 2m minus 1. Let us think that we are working in coordinates. So Clifford 2m minus 1 acts here. What is the dimension of irreducible representation for this guy? There are two irreducible representations, but they have the same dimension. Which one we see here?
plus and minus part of S.
Yes, the tricky part is that the dimension of this guy is bigger than that one, twice. So, what are the possibilities? There are nothing happens. All the representations are zero. Yes. So, but it's not zero representation because even part is doing something here. It acts non-trivially. It's possible that it contains one copy of irreducible presentation plus trivial part. I don't think so. But so this guy is splitted into two representations of this thing. It's splitted. And what is, I think, obvious, that if you take even odd element here, so element V, which belongs to, say, C to M, if you multiply this thing by one vector, this will interchange the order of these guys. Is it obvious or not? If you take one vector, which belongs to, which sits inside Clifford odd part. So if you take one vector, which sits in odd part of Clifford algebra, then it acts on these two summands, interchanging them. Is it obvious or not? This is a very simple question from my point of view, but I want to...
It's obvious if we believe in the graded isomorphism?
No. Without, we don't know about graded isomorphism.
But what are these S plus and then ones? Are not the same as...
So I want to prove this theorem. I'm not explaining it, I'm proving it. So what I did, let me repeat. What I do, I take even part of the Clifford algebra. I know that even part of the Clifford algebra is previous Clifford algebra taken as a whole. So even part and odd part, everything is here. But this considered as subalgebra here acts on Spinor representation. It acts, but its dimension is twice the dimension of irreducible representation of this thing. So this representation splits into two subspaces. And even part of the Clifford algebra lefts them invariant. So let me fix it on the blackboard. So if I apply Clifford algebra even part to subspace of the Spinor representation, then it is, the grading is preserved just for the simple reason because even part is just this algebra. The next question is, if I take just one element from odd, which is just vector, for simplicity, take a vector, one vector, and act by this vector on this splitting. My claim is it changed the grading. Plus is sent to minus, minus is sent to plus.
So
why?
multiplication by V should send irreducible representation to irreducible representation, since V times, say, S plus is stable with respect to even part of...
Yes.
Okay. So we need to...
And the initial representation is irreducible, so we...
Yes, that's the trick. The argument does not depend on the choice of vector V. It's a general situation because you can change the basis. You can take first basis vector as vector V. So for every vector, it should be so. Imagine that vector V preserves the representation. So plus minus is sent to plus minus. Then it means that Clifford algebra 2M preserves the splitting. That's why this is not irreducible, because it can be reduced to the smaller. So it's quite simple. So this is explanation why this isomorphism is graded, because Clifford algebra is graded, it splits into even part and odd part, and this odd and even part preserve this splitting in the way we need. Very good. May I erase? Sometimes people use representations of Lie algebras, blah, blah, blah. It's possible to do it from that way, but it's little. Then you need to know the theory of representations of SO. Do you need it? If you know, then it's okay. But if you are not very good with representations of Lie algebras, then you can go in this more or less straight way. And even if you know theory of representations of Lie algebras, I still believe that this way is very nice because it's quite simple and more or less you can write everything in a very direct way. So next way to produce representations of Clifford algebra is so-called twisting. So-called twisting. So what we want to do, we want to construct more Z2 graded representations of complex Clifford algebra. Imagine we have Z2 graded space. Superspace. Then I suggest you to consider if you want to speak about everything without coordinates, then you write this one. If you want to speak about coordinates, then you write this one. Because we want to apply this construction to each cotangent space, we prefer this way. Because at some moment we will write something like that. It means that we consider fibration of Clifford algebras. So we apply construction of complex Clifford algebra to cotangent vector spaces. So that's why we want to use coordinate-free approach. The question, how this guy is Z2 graded? So this is hat over tensor product means that this is a Z2 graded space. How to I would write it in this way. So grading J is SV alpha tensor W beta, and here we write sum A plus beta is equal to J mod 2. To be, as usual, if you want to write here plus, then you take two things, minus minus and plus plus. If you have here minus, you write two summands, minus plus, plus and minus. So this guy is graded space, and obviously Clifford of V is represented as in graded endomorphisms of this thing. Endomorphism over C. This is quite important to follow linearity on which ring happens here, because it will be important.
So if W has tensor product or a direct sum?
Where? Here? Oh well, is sum, sure.
And also, does Clifford act only on the left?
Yes, this I want to write a formula. So this is CW how the action is defined. You just take an element here, and it acts on spinor tensor with a vector here. So this guy is a sum of elements of such a form, and it sends this tensor product to where C of x applied to psi. So this one is spinor, x acts on spinor, and you do not touch W. This is a formula. It's so-called twisting by W. You can tell me, okay, where is the interesting thing? What you just tensored by W and nothing happens because W does not contain any action of Clifford algebra. Actually, it means that you take several copies of spinor bundle, indexed by basis in W. It's okay, that's very good. Very good point of view. But let me make this stuff more complicated. Each W, which belongs to the vector space W, defines a map of modules. Which modules? S to this. How I can define this morphism? Very simple. You take a spinor and send it to tensor product of spinor by this element W. It is Clifford of V linear because Clifford of V acts here from the left and here from the left, and this guy does not disturb you. So action is, so if you apply C of x to psi, then this thing is sent here, and this can be written in two forms. You can write parentheses here, or you can write them here. So this map is linear. We can denote it.
Сейчас. Также можно было с самого начала писать, правильно?
Что?
Это одно и то же. Сейчас написать. То, что сверху, то, что сейчас.
No, it's an action of this guy here, but this is a map from this one to that one. A little bit different.
That should be W instead of. Right.
Yes. Thanks. Now imagine that we have a linear map. Phi is a map from W to W. It's more important for us. If we have a linear map from W to W, then we can make it induced mapping. Phi tilde, which goes from S of V graded product with W to S. Okay? What is the formula for that? Guess? Psi W is sent to yes, sure. You do not touch psi. And you apply psi, phi, sorry, psi. you apply phi capital to W. This is a map. The question, this was C-linear. And what can you tell me about phi tilde? My claim is it is Clifford of V linear. After taking tensor product on the left with a bigger ring, I obtained linearity in this way. So, let me fix the results we obtained here. They are very, very important for us. So if you have graded endomorphism of W over C, graded means that, then I can construct endomorphisms over Clifford algebra, also graded of what? Each endomorphism of W induces endomorphism of this tensor product. Okay. Another way, if I take this thing and write here endomorphism over C of W, then I can construct endomorphisms of over C of this guy. Wow, that's enough. Please fix those maps and tell me, what do you think about them? Are they monomorphism? Are they epimorphism? We should make a claim, but we will not prove it. It's just some standard statement from algebra.
So maybe this is an isomorphism.
Yes, sure, they are isomorphisms. Roughly speaking, linearity over Clifford kills this part of tensor product. So we still have here only C linear. And this thing explains that Clifford algebra action is only on this part. So theorem, no proof. Theorem, no proof without proof. So it's proven, but not me. We do not discuss proof. These two maps are isomorphisms. Well, that's very important, but much more important thing is the following. Assume we have E. Graded Clifford of V module. Very simple question. Very, very simple question. Is it possible to represent it in this form or not? Yes, we still believe that V is 2m, to speak about Spinor representation and so on. So the question is it true that every module has this representation as tensor product. I will tell you, it's very stupid situation. Let me define E as Hom, graded Hom, over Clifford algebra from Spinors to E. If you're more or less acquainted with homological algebra, it's a standard way to remove a ring on the left-hand side. Okay.
So what is it that you just defined?
Oh, sorry, it's not E, it's W.
It's something, okay.
It's something else, yes, because otherwise it's wrong. Because this thing is much smaller than this one.
So we're kind of twisting E by SV star? Or?
Vice versa. You twist Spinor representation by graded space W.
Okay.
The question is it true that every graded CW Clifford V module is twisting of Spinor representation by something? This is the answer. So we take this one and exercise, check that if you take SV tensor with W, you will obtain E again. Okay? It should not be very difficult from my point of view. Well, notation. Notation is as follows. Instead of writing W, we will denote this by E over SV. So instead of introducing new letter W, we write S divided by S, because it's a little bit confusing, but it's very suitable. Imagine you have this expression. How to find W? You divide by SV, no problem. Nobody divides in tensor products, but it's just notation. The formula for W is given here. Okay. Hence, then we start from a linear map from Clifford module to Clifford module. So this one is Clifford V linear. Then look at the isomorphisms on the top side. If we have Clifford endomorphisms of this thing, what can we say about map of V using one of these two isomorphisms on the top? We use first isomorphism. If you can map E to E, then you have map from W to W. And this is bijection. That's why we have a map which is denoted in this way. It sends E to, actually this one is W, this one is W. First isomorphism gives us, instead of a map which is linear over Clifford algebra, map which is linear, just C linear. After you took W, there are no Clifford structure because elements in W cannot be multiplied by elements of Clifford algebra. Definition. Relative supertrace of L if you remember, in the Zinger formula, you'll seen Chern character with this superscript. It comes from this consideration. So let me repeat. So you take a linear operator, which is linear over Clifford algebra, and you want to calculate relative supertrace. Not this one, but relative. So you need to take into account structure of Clifford module. By definition, it is usual supertrace of the operator on the right-hand side. Relative supertrace. This will be discussed a little bit later. Okay, it's time to prepare to construction of Dirac operator. You know that Hodge-de-Rham operator, D plus D star, is a just very simple version of Dirac type operator. But to define more general case operators in more general case, we need to make some small preparation. Small preparation. Should I remind you what is a Spinor group? Yes? Okay, let's go. Let's go. Okay, let us speak about special orthogonal group. Everybody, I guess that everybody knows that this is a non-simply connected space. The fundamental group of this guy is equal to Z2. Yes? So there should be a group which is denoted by spin n, which gives us twofold covering of this space. So there's some kernel two elements. They have the same Lie algebra, so if you take tangent algebra at the unit is the same as tangent algebra at the unit of SON. It's just skew-symmetric matrices. But what I want to do, why I ask you about Spinor group?
This is independent of the parity of n.
Yes. It's independent of the parity of n. If you take indefinite form, so then pseudo-orthogonal group can contain four components of and then SO will contain two components. Well, nevertheless, what I want to do, I want to describe spin n directly. Definition, construction. I like this construction very much. So let us consider inside Clifford algebra, we will consider some specific collection of elements. V1, blah, 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 V2k, where the scalar product of V with itself is equal to 1. Spin n consists of such products. Very simple. The good question is to know, is it true that this thing is a group? What is an inverse element here?
The same thing in reversed order.
same thing in inverse order. So you think that V is equal to minus V in this case, because if you multiply V by minus V, you will obtain this thing is...
No, I think that he meant V2k times and so on, V1 in reverse order.
But I checked for one element. I checked for one element. One element. Okay, very good idea. So you know that there are two groups, special orthogonal and orthogonal. What is the difference between orthogonal and special orthogonal? Orthogonal is a little bit bigger. One also can consider group which has very strange name. So you take product of not of even number of elements, but arbitrary number of elements. And then you obtain twofold covering of orthogonal group. So my argument applies to pin, and also it applies to spin immediately. The question is, what is the unit in this group? Mathematicians would tell, we take a product of 0 elements. 0 is even, 0 product of 0 number of elements is 1, so 1 belongs to spin. But I'm not happy about that. How to construct unit here? Very simple. V belongs to spin n. It's a unit here. You take product of 4 copies of V. Well, as you told me, this thing inversed is minus, yes, it's okay. VL blah 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 V1 minus 1 to the power of L, okay. So inverse is okay. I want to construct a morphism from this one to SON. I can write a formula how pin n is sent to ON. I will denote it by A. So A sends X to some operator in Rn. It takes a vector V, okay, W, and sends it to the following expression. Okay, I will write it in this way, alpha of x. Alpha of x is parity operator, so alpha of v is minus v, alpha of v1, v2 is v1, v2. So alpha calculates its identity on even part and minus identity on odd part. So this is a map from elements of pin group to operators in Rn. What I want to check? I want to check that this thing is also belongs to Rn. First, alpha of x, wx minus 1 also belongs to Rn. Let us make a simple calculation for one vector, v1, v, w, v minus 1. This is for x, which is a product of one element. How to calculate this thing? First of all, we need to replace v to the power of -1 by this formula. This is VWV. Then you interchange the order, you obtain V squared. Oops. And this is wrong because you know that if two orthogonal vectors anti-commute, but two non-orthogonal vectors do not anti-commute, there is a contribution of scalar product. Very good. So let me write this formula. If you take this plus this, mental calculation. Tell me please, what is it?
-2 scalar product V.
Why?
Something from V.
Why two minus scalar products?
I remember something like that from last week.
Maybe plus
Or without minus.
or without minus? Okay, it's quite simple. Imagine that you take cross product. So you take coordinate I here and coordinate J here. You will see the same thing here, but in reversed order on the basis vectors. So they disappear. Okay? So the only thing which contributes to this, if you take coordinates with the same indices, V1, W1, V2, W2, all of them contain square of basis elements. They all came with minus. So you were absolutely right. This is two scalar products with minus. So here I interchange the order. So it's wrong. So I write here minus. But also I need to add here something. Minus 2 square product of VW with V. Minus disappears. W minus 2V W. Gentlemen, I believe you know this formula. What is it? This is a reflection of the vector W in the hyperplane which is orthogonal to V. Reflection of W in plane orthogonal to W. The reflection of W in hyperplane orthogonal to the vector V. So obviously this guy preserves scalar product. If you take this long product in spin group or pin group, so this is just product of reflections. So image of A consists of compositions of reflections. Very good. Very good question. Is it epimorphism or not?
Yes.
Why?
Because orthogonal group is generated by reflection.
Yes.
Hmm?
Sorry?
It is called Dieudonné theorem.
Cartan-Dieudonné theorem. It's very simple. What you do, how to imagine it. So, if you in suitable basis, this is a rotation by phi1, rotation by phi2, blah blah blah, and in the bottom angle you will see plus minus 1. This is the structure of orthogonal matrix. Rotation in 2 by 2 plane is 2 reflections. This is a 2 reflections, blah blah blah. So in suitable basis you will write these reflections in a very easy way. So this guy is epi. So A is, and hence A is on 2. What I'm interested in? I'm interested in the kernel of A. Let me erase here. I want to know something about kernel of A. My claim is kernel. I will not consider general case. I will consider only kernel of A from spin n to SON. It's a little bit simpler. So element in the Spinor group can be written in this form: 1 plus lambda ij ei ij. So you can write it in the way. Oh, sorry, it's just lambda. Lambda plus sum of ei times lambda I. Number of elements here is even. You expand it in a standard basis. Okay. If X is identity, what does it mean? Does it mean that W is equal to X, WX minus 1, WX is equal to XW? That means that this guy commutes with any vector. Let me try vector E1. Imagine you wrote this thing. First of all, you write E1 on the left-hand side, and you wrote E1 on the right-hand side. So EI and E1, lambda I. This is an expansion in the basis, so we should check summand by summand if they coincide or not. So this is okay. They do coincide, no condition. If I does not contain 1, then E1 EI is equal to EI E1. For what reason? Because you need to interchange E1 with elements of EI how many times? Even times. E contains no 1, and you need to interchange the order even times. So they are equal. So no condition. These summands coincide. Much more interesting happens if I contains 1. Then if you write this expression, what you will see? You can think of the following. You send E1 from left to right, but at one place you will see E1. If you interchange the order, no sign appears. So this guy has different signs. From this it follows in this sum there are no I with 1 belonging to this I. So this collection of multi-indices cannot contain 1. I checked. This thing should commute with multiplication by E1 from the left-hand side and right-hand side. E1.x should be equal to x E1. From this condition, it follows that there are no 1 in these indices I. But E1 is not unique. You can try E2, E3, blah, blah, blah. So it means contains no I at all. What is left? x belongs to kernel of A means that x is just lambda times 1. It's just a number. Not an element of Clifford algebra, which is written in very complicated, just a number. Just a number. Okay, let me left it as a simple exercise. Check that x belongs to kernel of A means that x is not just lambda, just plus minus 1. It's not very difficult, just plus minus 1. So kernel contains two elements. So kernel of A contains plus 1 and minus 1. And I will show you it in a moment that this twofold covering, which is written here, is non-trivial. Let me show you a path in spin group for n greater or equal than 2, such that so inside Spinor group I can join 1 and minus 1 by some path. It could happen that this group is just two copies of SON, one and another, and the projection is just projection. But it's more tricky thing. It's this thing inside this thing, two elements from kernel can be connected by a path. And the formula is given as follows. You take E1 and you multiply it by a vector of length 1, because in spin group you should take a product of even number of elements yes, it should look like this. What happens if t equal to 0? Gamma of 0 gives me E1 by E1, so it's minus 1. If I take gamma of pi, this will be cosine of pi, which is minus 1. So inside spin group there are enough room or enough space to join these 2 points by a path. But path is long because I went out from one sufficiently far away. Okay, that's all for today.